Hi guys, in lesson 3, we're going to talk about conditional probabilities, which we've already done, but now I'm going to put a name to it and kind of formalize this idea of a conditional probability. So students at Rufus King High School are discussing some of the challenges of finding space for athletic teams to practice after school. Part of the problem, according to Kristen, is that female students are more likely to be involved in an after-school athletics programs than males. However, the athletic director assigns available facilities as if males are more likely to. Before suggesting changes, the students decide to investigate. We have a little investigative reporting going on here. So at Rufus King High School, 40% of the students are involved in after-school activities. So 40% are involved. That's out of everyone. 58% of the school students are female. 58% of students are female. And 23.2% of everybody are female and do after-school activities. And yes, do after-school activities. So let's use these numbers to create a hypothetical 1,000 two-way table. So I don't know how many kids are at Rufus King High School, but I'm going to assume there's 1,000. So I need to, these probabilities need to get multiplied by 1,000 to create how many fake students I have. So 58% of them are female, so 580 of them are female, which for free gives me 420 of them are male, because those two margins need to add up to 1,000. 40% do after-school athletics, so 400 out of 1,000 is 40%, which leaves me with 600 out of 1,000 do not. 23.2 is female, and yes, so 232 goes there. So now we can fill in these missing pieces. We can quickly fill in these missing pieces. 348. I subtracted 580 minus 232 to get that number. I can subtract to get total male yeses. 400 minus 232 is 168. And then 600 minus 348 is 252. And just as a double check, I can add across and I get 420, so we're good. So what is the probability that a randomly selected student is female? I go to Rufus King High School. It's the probability I pick a female, 580 out of 1,000, which we already knew was 58%. That's just using the two-way table. What is the probability that a randomly selected student is female and participates in athletics? So this is the probability of female, and yes, they do athletics. So I'm still picking out of everybody. It didn't tell me to limit my picking. I'm still picking out of the 1,000. I'm randomly picking a student. So female and yes is right here. That's that 232 number we played with before. Here's a new number that we're going to have to find, though. What is the probability that a randomly selected student participates in after-school athletics programs given she's female? So I was given information here. I'm only picking from the females. So what's the probability? What probability am I actually finding here? Yes, they participate, given they're females. So notice my universe has to shrink here. I can't pick out of everybody. I'm only allowed to pick from the females. How many of them do after-school athletics? 232. 232 out of, how many females were there? I'm not picking out of 1,000. 580. So that given probability there, you have to create it on your own. 232 divided by 580 comes out to be a perfect 0.4. Perfect 0.40, so that's 40%. So that's how we can work with these two-way tables. I can just say find the probability of female. I can have you find an and probability. And is still out of the total. An and probability is still out of the total. A given probability shrinks your universe. A given shrinks your universe so you're not picking from the whole total. So what we've been working with is called a conditional probability. And conditional probabilities are given. The keyword for a condition, you have an extra condition thrown on your given information. You're not based on the whole population, but you're based on a subgroup. So given events A and B, we can find the probability of A given B, this vertical bar. That vertical bar there means given. A given B. This is one of the huge things that's going to follow us for the rest of this unit. How do I find a given probability? It's the and probability, but your universe shrunk to the given piece. Your universe gets smaller. So I want to know here, what's the probability of A given B already happened? So B already happened, so that's why the numerator is A and B. B already happened. I know B occurred. So even though I want the probability of A, I use the and formula up top. But I only divide by the universe of B. B becomes the universe and shrinks me down. So that's how we're going to work with conditional probabilities. You're going to use this formula. We're going to be using this formula a whole bunch over the next 3 weeks. So with two-way tables, we can think about finding conditional probabilities as zooming in on a row or a column. So here's a two-way table that shows the classification of students in mathematics by gender and dominant hand. Are they right-handed, left-handed, or ambidextrous? And I have their genders there. So what is the probability that a student in the class is female? No conditions. I'm just finding probability of female. How many females are there? 14 out of my class of 30. 14 out of 30 is about 46.7%. What is the probability that a randomly selected student in the class is female given that they're right-handed? So we're still finding the probability of female, but I was given that they were right-handed. So notice, my universe has just shrunk. I was given extra information about who I'm picking from. I am only allowed to pick from the righty column. That's it. From that subgroup, I want to know how many are female. So the right column, what's my universe? My universe is 23 people. How many of those 23 are female? 12. So 12 out of 23. So the probability of picking a female, knowing they were already right-handed, is 52%. So did knowing the student was right-handed affect the probability of picking a female? Well, look at it. It did. Yes, there's an association. Yes, knowing there is an association. Knowing the student was right-handed actually increased the probability of choosing a female student. By shrinking my universe there, I actually increased the probability of me finding a female from this class. Just as a quick little side note, how is this different? The probability of right given female. It looks very similar, but it's actually a completely different probability. Here, you're looking at your universe shrunk to these 23 men and women, and you want to know the probability of picking a woman out of that group. Over here, though, what's your universe shrinking to? What are you given? You're given they're female. So my universe shrinks to that row. So the denominator is actually 14 because I shrunk to that row. So on this one, my universe had men and women in it. Over here, my universe just has females in it, and I'm deciding are you a righty or a lefty. So that probability is actually 12 over 14. So notice that their numerators are the same because it's the and probability. It's that and number. But notice the denominators are different depending on that given condition. So you have to be careful when working with these given probabilities. That's the end of my side note. We'll keep going. We don't have that much more to go. Excellent. Why don't you pause the video and try this page on your own? Why don't you try these problems on your own for me? So what's the probability that a randomly selected person will vacation in New York next year? What's the probability they are going to New York? Well, 400 out of 1,000. 400 out of 1,000 are planning to go to New York. So I get 40% there. What is the probability that a randomly selected member will vacation in New York given, that's the key word of today, given they watch the ad? So my universe shrinks to I'm only allowed to choose from the people who watch the ad. I'm still finding the probability that they're going to New York given they watch the ad. So my universe shrunk. I'm only allowed to pick from the people who watch the ad. So my universe, my denominator, becomes 750. Of those people, how many are going to New York? 300. 300 over 750 is 40%. So do you think the ad campaign is effective? Well, if I just pick someone, there's a 40% chance they're going to come into New York. If I pick from the people who watch the ad, it's still 40% chance that they're coming to New York. The ad did not affect the probability of a viewer coming to New York. So knowing they watched the ad didn't increase or decrease the probability at all. It remained constant. So that given information didn't actually affect the probability, which in this real world case, that's telling me this ad is not effective. This ad is not making more people want to come to New York. It's a bad ad. They should probably change it around if they actually want to promote people, want to promote tourism in New York. Unfortunately, we're not always working with two-way tables. So let's do a little word problem here, and then we'll call it a lesson. So Mr. Hines determined that of the senior class, 15.3% of them are members of the drama club, 10.2% of them are in AP Calculus, and 1.5% of the senior class is in both. All right, so I got the probability of drama is 15.3%. The probability of AP Calculus, that's 10.2% of the senior class. And the probability of both, so that's drama and calculus, is only 1.5% of the seniors. So determine the probability of D given C. D given C. So what does this mean? I'm only picking from the AP Calculus students. 10.2%. 0.102 is what I'm actually going to go with. Right? This is actually 0.10. This is actually 0.015, and this is actually 0.153 because I have to work with decimals instead of percentages. So the formula, the conditional probability formula is the D given C. What goes up top? So if I slide back up here, what goes up top when I find a conditional probability? The and. It's not just the probability of A up top. It's the and probability that I'm going to be putting on the top of this fraction. So the probability of D given C is I'm only picking from the calculus kids. So I can't put all the drama kids up top because they have to be in calculus already. How many of them are also in drama? 0.015 out of 0.102. So if I divide here, I end up getting 14.7%. So what does this mean? How do I interpret these results? Given a senior is in AP Calculus, the probability they are in drama is 14.7%. Knowing they're in calculus, there's a 14.7% chance that they're in drama. So that's what this given probability is here. Given I'm in calculus, there's the and probability goes up top of 14.7%. One more and we're done. The probability that a new microwave oven will stop working in less than 2 years is 0.05%. I'm going to take some notes. The probability it stops working is 0.05%. The probability that a new microwave is damaged during delivery and stops working is 0.04. So damage and stops working, that's awful, is 0.04. The probability that a microwave oven is damaged during delivery is 10%. That's awful. They need a new delivery company. So I just read those and kind of took notes. Given a new microwave is damaged, so that's the given information here. What is the probability it stops working? So I want to know the probability that it stops working given it's damaged. So the formula A given B is and over the given. And over the given is how do I find a conditional, this given probability here. So the and probability goes up top. They both happen. Out of, I'm only picking from those that are damaged because that was my given condition. That's what goes in the denominator. So I end up getting 40%. If I know I have a damaged microwave from delivery, there's a 40% chance it stops working. That's what this probability we just found is. Knowing I got a damaged microwave, there's a 40% chance it stops working in the first 2 years. Got to send that microwave back and get a new one. So hopefully you feel good about this conditional probability. It's shrinking in on a row, but I need you to know this formula. The big idea is the probability of A given B is and both of them happening over that given piece. That becomes your new universe, that given piece, that becomes the denominator of your fraction. And if you want to know the probability of A given B, B already happened, so that's why it's not just A up here, it's A and B. See you guys in the next video where we play around with these conditional probabilities a whole lot more.